everybody. Today we are going to do some logarithmic function manipulation. And we're going to take some log properties and we can take one form and put it in another form that might be easier to work with. And we are going to use it again when we solve our log and exponential equations. And then when you are sitting in calculus again, some of these log properties will come back up for you. So I'm not sure who did what in Algebra 2, so I'm going to talk about this just a little bit. You have what's called a product property. So if you have a single log and you have two arguments that are being multiplied together, then you can do an expansion where you can turn that multiplication into addition. Example right here, I have log base 2 of 5x is the same as log base 2 of 5 plus log base 2 of x. Then right here, if I have a quotient, the argument is being divided, I can turn that into subtraction. So here with my example, log base 3 of y divided by 4 turns into log base 3 of y minus log base 3 of 4. And then we have the power property. If you have that exponential, it has to be only on the argument. If you have the exponential on the argument, it can become the coefficient of the log. So right here, log base 7 of 3 to the x is equal to, the x came around front and became that coefficient. And all of these properties, as we work through them, we're going to use them in our manipulations today. But again, as I said earlier, we're going to work with them as we move into log equations. Okay, so right here, it says for each of the following, write an equivalent expression by condensing each expression to a single logarithm. So as you go through the process, I have this coefficient, okay, so I can bring that around front using my log property. So I can say this is log base 2 of x cubed plus log base 2 of y. And I needed to move that coefficient because when I look at my property rules, I need that to be over here with my argument and not as a coefficient so that I can put them together. Then I notice I have an addition problem with the same log, so I'm like, okay. Then I can convert this into a multiplication. So log base 2 of x cubed times y. Okay. Then here, I have three logs, r base 10, remember also known as the common log. I'm going to work through this a little bit. It looks like I have subtraction, so it looks like I should be in a division situation. I'm going to take that 10 off. I'm just going to say log x minus, and I'm going to put this in parentheses, log 5 plus log z. So remember, if I factor out a negative 1, I can make it look like this. Because here I've got the negative I could distribute back through. So then I get log x minus, inside the parentheses, that's addition, so I can turn that into a multiplication. And now that I have a log subtracting a log, then I can turn that into my division. Right here, again, before I do any of my other manipulations, I'm going to convert my coefficients into exponents. I'm going to get log base 7 of a squared minus log base 7 of b to the 5th plus log base 7 and 4th. Now, I'm going to go, hopefully you'll recognize this, I'm going to go ahead and reorder the equation, but you might not need to do that. But I noticed that I have addition, so remember addition is commutative, so I can move it. Minus. My addition become multiplication, so I'm going to get log base 7 of 4 times a squared minus log base 7 b to the 5th. Subtraction turns into division, so I get log base 7 of 4a squared over b to the 5th. So that's when we take our expression and we condense it so that we're in a single logarithm. The other way is when we take a single logarithm and expand them out. Okay, this is the one you use quite often in calculus, is doing the expansion. So as you go through, you're still looking for, okay, multiplication is going to mean addition, division is going to mean subtraction. So kind of just thinking as you go through that. So right here, I'm just going to start off, okay, and see what I get. I'm like, okay, log base 4 of 5 plus log base 4 of x cubed plus log base 4 of y. And then when you do your expansion, you do not want to have an exponent in your expansion. So you're going to have log base 4 of 5 plus 3, so I'm bringing it around front so it can become a coefficient. So again, do not leave an exponent in your expansion. Go ahead and create that into your coefficient. Just a quick reminder, probably remember this, that when we have the square root, that's the same as saying that I'm taking this expression to the 1/2 power. Because this 1/2, the exponent is on the entire argument, I can move that around front and it can become the coefficient of the whole thing. So it's 1/2 times this whole piece. Now I have multiplication going on, so that should turn into addition. I've got a division, so I should have some subtraction. So I'm going to do my expansion. 1/2. I'm going to bracket this because I really want that 1/2 to go to all the parts. Log base 5 of x plus log base 5 of y. And then my subtraction minus log base 5 of z cubed. And we're not leaving an exponent in our expansion. So as we finish up, around to become the coefficient. And okay, if you leave it like this, you can also distribute your 1/2 all the way through. If you like to do that, you could have your final answer look like this. Become 3/2. Either way works for me. Okay, look here. Okay, I have some multiplication, I have some division, so I should have some addition and subtraction. So I'm going to start off the natural log of x to the 5th plus the natural log of y, and I'm going to take that square root to the 1/2 power minus the natural log of z cubed. Again, no exponents, so I'm going to move everything to become a coefficient. 5 natural log of x plus 1/2 natural log of y minus 3 natural log of z. Okay, so you're just going to kind of fiddle with this, whether I ask you to take what's an expansion and condense, or a condensed into an expansion. Okay, so we're going to practice with those. A multiple choice question could look like this, which of the following is equivalent? If it was me, I'd probably just start working the question, say, okay, it looks like it's going to be division, so in its division, so I should have some subtraction. That coefficient around front. And then I would come over and see if I could find my solution, which looks like it's C. Okay. The function f of x equals log 6x is a horizontal dilation of the function. Okay. Remember, it's a horizontal dilation because they're multiplying by the 6. Remember, it's a dilation by 1/6. Okay. Show that f could also be written as a vertical translation. Okay. Well, all I know to do is to work with my log properties, multiplication. Can turn into addition. And then right here, you don't know the exact value, but you know log of 6 is some type of number. So that would be my k, that would be my vertical translation, the f log 6. Okay, let's look at a couple of other pieces. So you do have your change of base, where if you have log base b of x, you can convert it into any other type of log, okay, with whatever base you need. So this one they just converted log base a of x, log base a of b. Notice that the argument becomes the numerator and the base became the denominator. So right here we have a question where we're going to work through. It says, let f of x equal log base 4 of x and g of x equals log base 9 of x. And they want us to show that f is a vertical dilation of g by finding the value of k such that f of x equals k times g of x. And that's a lot going on right there. So let's kind of talk about what we know. We know f of x is log base 4 of x equals k times, and then g of x is log base 9 of x. So they want us to show that f is a vertical dilation of g, so we're going to have to deal with that a little bit. So since we noticed that g is in base 9, it would be helpful if I got f of x into base 9. Okay, so I'm using my log property, my change of base up here. So f of x can turn out to be, okay, so we would have, since we want it base, so we would do log base 9 of x over log base 9 of 4. So all I did was do that change of base right there. Okay, so I've converted, here's my f of x, so now I'm going to come back over here, and it says we want to show that f of x is a vertical dilation. Well, notice I've got k times g of x. So f of x right here, if I keep going with the idea of f of x, then I can separate this out. I could say this is 1 over log base 9 of 4 times log base 9 of x. I've just split my fraction up. Well, g of x was log base 9 of x, so here's my g of x, and then here's my k. We don't know that value, but we know 1 over log base 9 of 4 is a constant value. So I have shown by taking my change of base that I can have a vertical dilation right here. Okay. Last class period, we talked a little bit about the natural log. It had a base e. Okay. And we talked about log base e of x as the natural log of x. We rarely see it in this format right here. Every now and then you do that if you need to manipulate something, but in general you're only going to use the natural log of x. The properties work exactly the same as they would with any logarithm. So right here, if I'm trying to find an equivalent, hopefully subtraction to you is now beginning to mean division. The coefficients can come around and become exponents. So subtraction is going to turn into division. Looking for the term that matches that, which is a. Now, when we do that condensing, okay, please make sure that you're condensing. You don't have the natural log written twice. It's just the natural log of whatever the argument turns out. Okay, we have talked about how we have inverses between exponentials and log functions. And here is your general form for an exponential function with all the translations in there. Same thing with your logarithmic function. And we're going to kind of talk about how would we go about finding an inverse, okay? So a few little steps right here. Of course, we're still going to switch x and y. We're still going to solve for y. we're just going to have to go through some manipulations, and of course our final answer will be written in the correct format. So there's not a lot of space here. So I'm going to rewrite this so that f of x is y. So I'm going to come over here so I can get some workspace, and I'm going to switch my x and y. So x equals 3 times 2 to the y plus 4 minus 15. And now I need to get that y to that y somehow, so I'm going to have to work until I can get there. So of course the first thing I would do would be add 15 to both sides. So that'll give me x plus 15 equals 3, 2 to the y plus 4. And we're just unwrapping it. We're moving everything I can move around so I can get to that piece right there. So I can get rid of the 3. I can move that 3 over by division, so I can say x plus 15 over 3 equals 2 times y plus 4. Okay. Now, one of the reasons we care about those properties where we have an exponent is I have to figure out how to get that exponent and the y out of the exponent position. The only way I'm going to be able to do that, so I'm going to come back over here, is I am going to log both sides, and I'm going to log both sides with whatever the base of my exponential is. So base 2, so I'm going to say log base 2 of x plus 15 over 3 is equal to log base 2 of 2 to the y plus 4. And hopefully you will remember a little bit about what happens when you have the base and the exponent. But what I really want you to remember is when I do that piece right there, okay, I can bring my y plus 4 over, times log is base 2 of 2, which is 1. And then to get y by itself, I'm going to subtract. I'm actually going to put the negative 4 in front, just so it doesn't get mixed up in the log. But recall, that would not be full credit. The inverse, you would need to say f inverse of x is equal to negative 4 plus log base 2 of x plus 15 over 3. So that's when we had our exponential. We wound up logging both sides. Here, I'm going to work through this also. I'm going to take g of x into y, so y equals negative 3 log base 5 of x minus 4 plus 6. Oops, sorry, I'm off the screen. Switch my x's and y's. And again, I'm going to, oops, didn't change my x to my y. And so I need to get into that y, so the first thing I'm going to do is I'm going to subtract 6. Trying to get the log by itself, so now I'm going to divide by negative 3. And then I'm going to use my conversion, and I can turn this logarithm into an exponential, the base 5, so I'm just going to do it again. So 5, so the x minus 6 over negative 3 is going to equal y minus 4. Then I add 4 to both sides. Of course, I want to correct notation with the correct variable, so I'm going to say g inverse is equal to 5 to the x minus 6 over negative 3 plus 4. And then last but not least, let's talk about what it means to be an inverse. It says let h of x equal 3 to the x plus 1 minus 2, and k is the inverse. And so it says, for what value of x does k of x equal 1? Well, remember that inverses, we switch our x's and y's, so I think what I'm going to do is I'm going to figure out what h of 1 is. So h of 1 is going to be 3, 1 plus 1 minus 2. So 3 squared, so h of 1 is 3 squared minus 2, which is 7. So if I know h of 1 is 7, well, if they're inverses, then k of 7 would have to equal 1. So I know that the x value that I'm looking for here is x equals 7. Okay, I want you to work hard working on the manipulations, making sure you're taking care to get them in the correct format, and I hope you guys have a great day.